Welcome, and thank you for standing by. At this time, all participants will be on listen only until the question and answer session of today's conference, at which time you may press star 1 and ask a question. Today's conference is being recorded. If you have any objections, please disconnect at this time. I'd now like to turn the meeting over to your host, Nikki Grimsley. Ma'am, you may begin.
Thank you very much. Good afternoon, everyone. Welcome, and thank you for standing by. All participants are in a listen-only mode until the question and answer session of today's webinar. Today's call is being recorded. If you have any objections, please disconnect at this time. I am Nikki Grimsley with the Clinician Outreach and Communication Activity, or COCA, with the Division of Emergency Operations at the Centers for Disease Control and Prevention. We are delighted to welcome you to today's webinar, Drivers of Infectious Diseases, Connections Matter. COCA is excited to offer this special call series with our partner, the American College of Veterinary Preventive Medicine. We are pleased to have with us today Dr. William Karish. CDC, our planners, presenters, and their spouses and partners wish to disclose they have no financial interest or other relationships with the manufacturers of commercial products, suppliers of commercial services, or commercial supporters. Planners have reviewed content to ensure there is no bias. This presentation will not include any discussion of the unlabeled use of a product or product under investigational use. At the conclusion of today's session, you will be able to identify key drivers of zoonotic infectious disease emergence, describe approaches to identifying risk factors for zoonotic diseases, and describe the difference between disease occurrence mapping and correlation-based disease risk mapping. At the end of the presentation, you will have the opportunity to ask the presenter questions. You may press star 1 on the phone to put yourself in the queue for questions, or you may submit questions to the webinar system at any time during the presentation by selecting the Q&A tab at the top of the webinar screen and typing in your question. Our presenter today is Dr. William Karish. Dr. Karish is the Executive Vice President for Health and Policy for EcoHealth Alliance. He is also the President of the OIE Working Group on Wildlife, and he chairs the International Union for the Conservation of Nature Species Survival Commission's Wildlife Health Specialist Group, which is a network of hundreds of wildlife and health experts around the world. He serves as the Inter-Project Liaison for the USAID Emerging Pandemic Threats Predictor program and is a member of the World Health Organization's International Health Regulations roster of experts. In 2003, he coined the term One Health to describe the interdependence of healthy ecosystems, animals, and people. He has led programs and projects in more than 45 countries and has published more than 160 scientific papers and numerous book chapters, as well as written for broader audience publications such as Foreign Affairs. At this time, we welcome Dr. Karish. Dr. Karish, please go ahead.
Right. Thank you, Nikki. It's a pleasure to have all of you online, and good morning and good afternoon, depending on where you are. I think I'll just start right in, and unfortunately I cannot control the slides, so I'm going to be asking Nikki to advance them for me, but I think everybody will get used to that after 2 or 3 slides. So why don't we go ahead and start. The title slide. I really have a second title, and then you see the disclaimer at the bottom from the CDC that I'm not representing the views of the CDC, but at the same time, my second title for the talk is really let's not believe everything people tell us. And I'll get into that a little bit because I think things I learned when I was in school and even things we've seen published a few years ago on a regular basis, those are certainly being overturned and we have new findings. But today I really want to, and if you go to the next slide on zoonoses, get into some of the things that are driving the emergence of zoonotic disease. And I don't have to explain what those are to you, but I just did want to give this reminder that they are a significant burden of disease on the planet. So the conservative estimates we have are about 1 billion cases in people, and some publications have even gone up to 2 billion cases, but it also depends on how you define a case and how you define a zoonotic disease. In any case, there are certainly millions of people every year that are dying of zoonotic disease. Next slide. So there's many ways people are being able to look at these, and this is kind of a connection chart, a network chart of how different zoonotic viruses, just the viruses, not bacteria or parasites, are linked between humans with either domestic animals or wild animals. So it's kind of a complicated view, but it does kind of show that there's a subset that we think about with domestic animals. And you see marine mammals are really out there as an outlier. But the majority of this network of viral sharing is with wildlife. And on the next slide, you might be more familiar with some of this data that's been kind of circulating for a while. This is some early work from EcoHealth Alliance on the analysis of patterns of EID events. This is temporal patterns. So we see the change over the last 50 or 60 years that emerging infectious diseases are going up. A majority of those, as you see, are actually zoonotic. So the blue ones at the bottom are the non-zoonotic. So we have this kind of rise in zoonotic in emerging infectious diseases. And the link to wildlife is a large percentage. So nowadays we talk about 70% of these new emerging infectious diseases somehow linked back to wildlife. So that's kind of some of the underlying data that we kind of are starting to see now. If you go to the next slide, there's so many ways, and I'm going to kind of repeat this theme throughout the discussion of the talk today, about how to illustrate what we have for data and how to analyze it, of course. So this is also from Kate Jones's paper that we did many years ago on the spatial patterns in EID events. So if you look at this in a very traditional approach, you say where were all the emerging disease events taking place, and you map that out, and we would have a tendency to say, well, this then is the map of where the hottest or riskiest places are in the world. But doing that, if you take historical data and analyze it or map it, what we have really is just a history lesson, and it's heavily biased by reporting. So this distribution has probably as much to do with reporting bias, who's actually published a paper on an emerging disease event, than it has to do with a disease event at all. If you go to the next slide, please. If you start to eliminate some of that reporting bias, so this is from some of the more recent work, so we've kind of moved on to what we call hotspots 2, you start to get a risk map based on the underlying drivers. And that's done by each of those emerging disease events. You go and study back on that event and see what are the characteristics, the ecological characteristics, the anthropological characteristics, socioeconomic characteristics that go along with that emerging disease event. And then you forget about the events and you start to map out where the key characteristics are. So then we get a predictive model of risk, and it's a relative risk. So in this image you see the orange or the redder zones are a higher probability or risk of a emerging disease event. And you can see on the bottom there the various factors. So we looked at about 250 globally distributed data sets and picked out the ones that seem to correlate with these emerging disease events. And you can see the relative influence there. So things like population, mammal diversity, biodiversity, but particularly mammal diversity, population, land use change, here it's characterized as pasture use change, I'll show you that a little more, are really the things that have the biggest influence on where emerging diseases are most likely to occur. Now, of course, it varies by region and it varies by the type of disease, but this is a kind of a generalized view to start saying if you're interested in targeting emerging disease surveillance, certain places are more valued for targeting than other places in the world. And that starts to come out in some of this predictive modeling, rather than looking at the historical perspective, which I said before is really biased by reporting. So on the next slide, what's going on and kind of the underlying theme that is going to behind what I'm going to be talking about today is the fact that diseases emerge, and particularly the zoonotic diseases emerge, basically on the same principles of evolution that have been working for millions of years. So the underlying principles of ecology and evolution of infectious diseases, or antimicrobial resistance, or other things, that involve life form biology, are the same. What's changing now is kind of what we're doing with the environment. And so it's like we're changing the playing field, or we're tilting it in one direction or another. So if we're imagining a soccer game or a football game, the rules aren't changing in the game, but the way that the playing field is shaped are changing, and that's what we're doing on the planet right now. So we have pretty dramatic changes in the last 100 years. So we're calling it the Anthropocene. Some people refer to that as this era now in time where humans are tending to dominate the landscape, and we're affecting not the principles of evolution, but the way that we're seeing things evolve. Next slide, please. One of these is, of course, the changing of land. And that's probably the most dramatic. So this is a slide of a 100-year gap on land devoted to pasture. And this 2001 on the right is what we used in that original hotspots model. But now we have data sets that showed the change every 10 years. So we have decadal change, and that's giving us higher resolution. And for a lot of the new data sets that are available, thanks to satellite observation data that's much better than it was 15 or 20 years ago, we're starting to get a clearer and higher resolution view of what's going on the planet. Next slide, please. So this is kind of reflected, if you can see, just the resolution between the old hotspots model, the risk of disease emergence, and the one on the bottom, which is the newer model, which we've included some new data sets like livestock presence and land use change, and you get a more refined view. Or if you go to the next slide, you'll see for a particular region, this is Southeast Asia, you can see that everything's not as red as it used to be. So it gives us a little more refinement on targeting surveillance, targeting prevention programs, targeting research. So we've a lot of the donor agencies, research agencies are actually using this in a practical application to say where should they invest their resources, where's a higher risk, and to really guide it, because there's certainly not enough money or time or people to work evenly across the planet, so we do have to be judicious about deciding where it is we want to work. If you go to the next slide, this is a little different approach where we've taken every paper, every published report of an emerging disease event, once again, over the last 50 years or so, and we used what came from the U.S. Institute of Medicine. They came up with some definitions of drivers of disease emergence 20 years ago. So rather than reinventing those definitions or making up our own, we went with the definitions provided by the IOM, just as something that was kind of neutral and wasn't biased towards our particular work, and went through every of these EID reports and scored them where they fit in these categories. So it's a little different approach than I showed you before, but you see on this one where land use change and agricultural industry changes are kind of the highest percentages of underlying drivers, what's behind some of these EID events. International travel and commerce, again, comes up at the top. That's that third bar. And that's, once again, because that's not so much the disease emergence from going between an animal or person or even in a person, but EIDs are also defined, of course, by a known disease occurring in a new region. So Zika virus emerging in the Americas is considered EID, even though it's a virus and a disease we've known about for 60 or 70 years. So that travel and trade works in there. Medical industry change has come along in the recent years. This probably has a lot to do with implants, but mostly transplants, more commonly, war and famine. So some of these things. I like to show this chart because for about 20 years of my work, I've had a big focus on bushmeat or wild animal meats, particularly in Africa. And so we know bushmeat's linked with HIV/AIDS. We know it's a kind of the original cause of spillover for Ebola events. So there's some pretty dramatic diseases. And in my mind, because of my personal professional bias, I always thought bushmeat was probably one of the largest drivers of disease emergence. But lo and behold, when we take an objective approach, and I have to admit that, I've been wrong for many years, if we look at this quantitatively and objectively, things like bushmeat actually fall down very low on these drivers of disease emergence. It doesn't mean they're unimportant. We wouldn't say that HIV/AIDS is an unimportant disease. It's just that in the number, that relative number of events, bushmeat doesn't shake out the same way that land use and agriculture and international travel and trade does. Now, on the next slide, I was saying those are kind of big generalities because in every country it's really different. Now we're starting to get in I'm going to start walking a little here on some thin ice because if we divide up the 200 or 250 so emerging disease events over the last 50 years, the number per country starts to get very low. So we still see kind of some patterns. So you see in Central Africa, there's a little more red and pink and purple, so that's war and famine and bushmeat. Whereas in North America, that's not how it breaks down. We don't see diseases emerging from bushmeat or consumption of wildlife in North America. Lucky for us that we eat deer and we go fishing, and there's just not too many new emerging disease events that come from the common animals that Americans tend to eat when they go hunting or fishing. Next slide, please. Another way to break down the same data is to put it into transmission pathways. And this is another kind of trying to use the analytical work for some practical implications. So we see that the types of transmission pathways, sometimes grouped by diseases, that at CDC, diseases, they tend to have specializations around vector-borne diseases or respiratory diseases, and that makes a lot of sense clinically. So when we kind of start to break those down this way, foodborne diseases, we can see that the types of drivers have different characteristics for the types of disease pathways that are linked to them. So land use change is highly represented by vector-borne diseases. Agricultural industry change, more about direct animal contact and oral transmissions, which would make sense because we're thinking about food animals and food production there. And medical industry changes as kind of the direct animal contact. I think in that category we also have laboratory workers that have new diseases have been identified in lab workers with they're handling animals. So maybe some cases of Marburg would have been linked to that, or other laboratory primate or laboratory rodent diseases have gotten into people. It's not just interesting academically. For us, it means that as areas are being developed, let's say in South America or Africa or even in the U.S., if forest is being converted to pasture, or forests are being converted for forestry and then there's a mining operation, the types of diseases we can expect to see there would fall in that land use change category, which are vector-borne diseases. So the kinds of surveillance systems that need to be put in place, or the kinds of preventive medicine that needs to get put in place, should be a little biased towards vector-borne diseases to be most cost-effective. So we can have vector control, mosquito control, those kinds of things in a mining or a forestry operation. Whereas in agricultural industry changes, if that's happening at a given location, we can start to say, well, we need to have better sanitation, better education for the workers, those kinds of things. So the interventions start to look a little different, and the prevention strategies start to look a little different. So it gives us some clues about where people should focus their efforts in different kinds of situations. And if you go to the next slide, please. Now, we can do this for a variety of different things. Most of the ones I've been showing you earlier were zoonotic, emerging zoonotic diseases linked to wildlife. But you can do the same type of analytics on vector-borne diseases, that's the bottom right, or drug-resistant pathogens, that's on the bottom left. So the trick, once again, and the reminder is that not to be just overwhelmed or swayed by the historical data, because that's very heavily biased by reporting, but to look at the characteristics underlying those events and then map out where those characteristics also exist. In what situations do they occur? Because without those underlying situations, the probability of this disease event occurring are very low. Next slide, please. This is kind of a look at breaking down that same approach I showed you about the drivers of emerging disease for foodborne infectious disease events, emerging infectious disease events. Then it shifts a little so that land use change drops down lower, but food industry change goes up. This is pretty intuitive, but as I said before, I used to think bushmeat was so important. So this kind of confirms our intuition about what's doing it. But it also says, where we can be targeting our efforts. So working directly with food industry, we can really reduce the number of these events rather than saying it's a personal hygiene effort there. And the next slide. This might not surprise some of you. It caught me a little off guard because I do a lot of work with viruses, and I realize, well, for foodborne illnesses, viruses just really aren't that important as bacteria. So once again, trying to add some objective nature to the kinds of things as we discussed and letting go some of our personal, professional biases based on, where we've spent years working. Foodborne illness. Unfortunately, you won't be able to see this video, but there's just this slide. And this is a typical market in much of the world. So probably millions of people on a daily basis are still buying their food in live animal markets. This one happens to be in Indonesia, and on the table there are domestic dogs. Below that table, I'll just describe the situation to you a little, are live dogs. So the customers will come, they'll pick out a live dog to make sure it looks healthy because there's very little refrigeration available. And if the dog is dead or the animal is dead, of course, the purchaser, the customer doesn't know if it was a healthy or a sick animal. So one way that they protect themselves traditionally is to go to a live animal market so they can see the animal before it's killed and prepared for them. So these are dogs being prepared. On this video, I next pan to the left, and then there's pigs and pork. And then to a table a little further to the left are fruit bats. So somebody's selling hundreds and hundreds of fruit bats. And a little further is the chicken salesperson, and they have several hundred to 1,000 chickens. And then someone has fish, and then somebody else is selling rodents, so they might have 100 or 200 rodents that have been brought into the market. And all these animals are killed, and you see blood everywhere. They take the entrails, so they'll clean out the viscera for the customer, and then they'll feed that either to the dogs or they'll save that later to give to the pigs. So the opportunity for viral dissemination or bacterial dissemination or any type of pathogen is pretty high. And people are walking around in this market wearing flip-flops, and with their bare hands they're touching food, and then they're taking those products and going home and taking it home. So I kind of use this slide to say the only thing that seems to be surprising about these emerging disease events, or that the fact that infectious diseases spill over between animals and humans, the only thing surprising about that is that we seem to be surprised every time it happens. because the volume of this kind of trade is massive. So this is, like I said, in markets throughout parts of the world, Asia, Africa in particular, somewhat in South America, and those are areas of the world with billions of people. So I'm really kind of surprised it doesn't happen more often, but these are very low probability events. So you go to the next slide, please. This is a typical picture of Ebola, hemorrhagic Ebola virus disease. And this is kind of what we all kind of learn about, you know, this is what happens when you see this disease. Well, this is kind of what happens later on after the outbreak has started to go on for a while. If you go to the next slide, this is where Ebola hemorrhagic disease tends to start out. And I don't know, Nikki, if the 1 billion kilos is up there, or if you have to click it again. But the volume of bushmeat, this is just for Central Africa alone, the volume of bushmeat is tremendous. And that's a gorilla that's being an arm of a gorilla arm and chest that's being sold. In that picture of that community, that's a logging camp in the Congo, Republic of Congo. And this is a very kind of a typical logging industry camp. The company that owns the logging concession, that they have the rights to the land for the logging, they will come in and build housing for their workers. There might be 3,000 or so workers that are brought into a very remote area of the forest where very few people lived before. To the left of that community, where the kind of the ramshackle kind of community on the left, are all the other people that start to move into the area to supply products to the workers, because the workers are getting paid cash, so a little cash community grows up around there. So you have sex workers, you have people selling soap and alcohol and tobacco, and then you have to have people that are selling food. But since these are in remote areas, the most accessible food comes from the forest, hence this consumption of bushmeat. So you'll have whole hunting communities that will be working the forested areas around the logging concessions, and at the end of the day, they'll come back with fresh meat for the workers to buy and process. So this is kind of the typical scene in forestry, and it gets back to those earlier sets of data I was showing you, where what are the underlying drivers for these disease emergence. So when we say land use change is associated with disease emergence, it's not that cutting down the tree makes a disease break out. It's this kind of underlying behavior and activities that are linked with that land use change pattern that allows or facilitates disease emergence. I did say these are really rare events. So what we have is, let's say the probability of Ebola coming out of an animal and starting a spillover event in a human population, then it goes human to human. But what about that first step? What if that probability, and I don't know what that number is, but let's say it's 1 in a billion, you know, a very low probability event. But we're talking about billions of kilograms of meat being consumed in the belt, if you'd say, the area across equatorial Africa where we know Ebola probably lives in animals. They have billions of kilograms a year. So the fact that we get one spillover event into a human every few years makes perfect sense, even an extremely low probability, because we've really kind of overwhelmed the odds. It's like if you bought 1 billion Powerball tickets next Saturday, you bought 1 billion tickets, your probability on any one ticket is just the same. But there's a good chance if you bought 1 billion tickets, you might win the Powerball lottery. And I think that's what's going on, why we're seeing these disease events, because I don't think we have the appreciation of the volume or the scale of risk and exposure that's really going on. So what seems to be a strange, rare event, in fact, is not very strange at all. Go to the next slide, please. We've kind of done some other analyses too, and this is kind of as you start to map the similarity of diseases amongst countries. So this gets into more about the spread of diseases and who's focusing on what. And so we call it kind of the biogeography of zoonotic diseases, or down below is just the biogeography of viral diseases in general. They don't have to be zoonotic. And what this shows is neighboring countries, different regions of the world have a different kind of list of diseases. So if you're going to go work in Africa as a clinician, your list of diseases that you're going to see every day and be dealing with and need to be familiar with is a different list of diseases than if you're working in North or South America. And the neighboring countries share those more than others. But it also explains why we kind of seem to be surprised or ill-prepared for what's happened in the last 50, 100, or 200 years about global trade and travel. And now we have these mechanisms that allow the movement of these diseases and the introduction of diseases outside of their traditional ranges. So I think this map, we're going to start to see over the next 100 years more of a blending or a homogenization of what's traditionally been seen in our community, in the health community, as something that kind of almost made us feel safe. So I think there's a false sense of security we have, and something that we need to be aware of. If you go to the next slide, you can actually calculate the relative risk of the movement from certain places to other places. So this is a mathematical model, and we started this one with the Jones hotspots that I started my talk with. And if you have passenger data, you can put in some other factors about what might affect it. And then if you go to the next slide, you can calculate the relative risk or probability of emerging infectious disease arriving at a given airport in the world with a passenger. So this would be an infected passenger arriving on an airplane. And certain airports have higher risk because of their connectivity with the hotspots, the places in the world that are more likely to have these emerging diseases. So you can see the airports in Asia tend to be redder because they are more closely connected with those Asian hotspots for emerging diseases. Whereas you come to North America, certain cities and certain airports in North America are much lower risk because of the direct connections to higher risk parts of the world don't exist. And then you can see kind of the East Coast down in Florida and California, and some in the upper Midwest and Texas, where there are more international flights, show up as a little higher risk. Once again, it helps you in kind of targeting where you're going to invest your resources or your dollars, or if you're in practice, where you might want to be paying a little more attention to diseases that are not traditionally in our communities, but might exist in other parts of the world. Next slide. I don't know how this is projecting to you, but for me, I'm seeing all the dates on there. But about 2 years ago, we ran using that formula that I just showed you on the risk of spread via air traffic. We could project out which countries in the world were at highest risk of a person with Ebola arriving in that country. And so this one is based on Guinea, which is a little tiny purple country right in the middle, and they're in West Africa. And then we projected out, and Nikki, you might have to click through if the dates aren't already showing. We did this in late July, the end of July, and we shared this pretty widely with our partners around the world. And then I have when Ebola-infected people actually did arrive following that. So all through July and August and September, and they tended to arrive in those countries that we predicted at highest risk. Not that we're so wonderful, but what I'm kind of trying to say is you can actually use a quantitative, analytical, statistical approach to dealing with this. The insurance industry has been doing this for many, many years and making lots of money. So we know that predictive analytics are effective. And, we're trying to apply it to some things that are useful to us in the health profession to be able to do this. This system is now online and publicly available. And you can you can start in any country and particular disease. It doesn't even have to be a disease if you wanted to say where's the risk of illegal shipment of something with an airline passenger, you can calculate that too. And then CDC also has a proprietary system. It's very similar. The results that come out of it are very similar, but that's only available for U.S. government staff to use, but ours is publicly available, and I can send you a link to that if you want to play with that sometime. And it's based on it's really based on passenger airline data over the last year and over the last month, and it'll calculate risk for you. Next slide, please. I want to zip through these. We also, some of the work I've been talking to you about is based on this, we call it host pathogen database, HP3 database. And we've kind of once again reviewed all the literature, and we picked out 600 viruses that are found in mammals, and we identified every mammal, including humans, that was infected in, and we have these virus-mammal relationships. So we can kind of use this to say that once you start to know where all these animals are in the world, it's another way to kind of map out where these spillover events or these diseases might emerge, or susceptible hosts in case a disease is introduced, because you have related host species in different parts of the world. So if something came to the Americas, you know, which primates, and we know that primates actually for Zika virus might be able to maintain it like they do, primates do in Africa. This next slide, if you do, when we break that down, what we do see is three kind of taxonomic groups of mammals share the most viruses with people. And those tend to be bats and primates and rodents. For one reason is the taxonomic group of rodents is huge. There's probably over 2,000 species of rodents. And for bats, it's quite large too. There's over 1,000 species of bats, maybe 1,400 bats. If you go to the next slide, it has to also do not just numbers, but also our genetic relatedness. So humans share more viruses with non-human primates, of course, we're more closely genetically related, but also bats and rodents are more closely genetically related to humans than other animals like gazelles or kangaroos or on here platypus. So as you get further away from us genetically, we share fewer viruses. So that also tells us which species we have to be more concerned about as a risk factor, or if you wanted to target surveillance, you know which species you can target your surveillance. You can also use some of these analytics to kind of jump into future projections. So on this next slide is climate change and emerging diseases. It kind of says, here's a virus, Nipah virus, which we know is in Southeast Asia. As you know, it's the reservoir is in bats, and it gets into swine, into pigs, but it also gets into humans, causes a hemorrhagic disease. It's highly fatal. There's really no treatment, and there's no vaccine or prevention. So we said, okay, what if Nipah virus, and what would the ecological niche for Nipah virus be in 30 years from now, given certain climate change scenarios? So we used the standard scenarios. We didn't make up our own. And we start to identify what parts of the world would be potentially suitable if that virus got introduced in the future. So it kind of starts to say, if you think about invasive alien species, this is kind of a similar thing that you can start to do with diseases to get people to start thinking ahead about this travel and trade, international trade and travel, and some of the risks that come along with that and what we might want to do to prevent the spread of disease. Next slide, please. So it looks like this is good. I have about 10 or 15 minutes. I wanted to kind of pull what I've been talking about together and use leptospirosis kind of as somewhat of a case study. It's not a virus, obviously, but so it gives us an opportunity to talk about something that's a little different, but it's also, I'm going to give a U.S., North American U.S. example or spread story to this. So I don't really have to explain the background to lepto for you, because I'm sure you all understand this disease. What we were able to do was get data that was available from IDEX laboratories for canine leptospirosis testing. So this data relates to canine leptospirosis but I think by the end we'll see that the underlying drivers are independent of the host. So you can think of this as somewhat species neutral, even though our preliminary data, what we've been working with, is from dogs, and it's a nice kind of robust big data set. So we have, this is testing coverage. This is not positive tests. This is just testing coverage. So where people, clinicians, in this case veterinarians, submitted samples for testing either microagglutination, which is a serology test, or PCR, which was the test for positive antigen, actually being leptospirosis, shedding leptospira at the time of the test. If you go to the next slide, if you break that down by the different test types, you can see it does vary a bit. So this is the microagglutination. The serology testing gives you kind of this pattern for the U.S. And if you go to the next slide, it has a little comparison, but we did some analytical work there to say where are the clusters of these positive tests. So you see the distribution's a little different, but these clusters are above the expected, or in orange or red, or blue would be below the expected if it was randomly distributed across the United States. So you start to see some people say, okay, this is starting to give us the hot spots of disease. But once again, remember, this is very biased on where we have test results. And on that original map, you see that the people didn't even submit test results from parts of the country. So to jump into this and say these are the hotspots of leptospirosis would be very misleading, even though these are the hotspots for positive MAT results to one particular laboratory. So we always have to be careful in making sure we're very clear about what assumptions are there. We also tried to calculate dog population data to somehow normalize those results, because in one part of the country where we're seeing a lot of positive tests, it might just be because there's a lot of dogs. So there is no existing dog population data by county, so we extrapolated that because we were able to get dog population data by state. And then we worked out the number of dogs per person in different communities in different states, and extrapolated that then to all the counties in the United States based on the human demographic data, and making some assumptions about the numbers, the average number of dogs in either rural settings or urban settings, and be able to work out. So we kind of have a cleaner map of dog populations by county in the U.S. that we could start comparing some of our test results with. The next slide, you start to get a little different. So when we use it by dog population, these same test results that I showed you before, you start to get a little different image of the distribution of the disease when it's actually corrected for the number of dogs. So we're getting a little closer to knowing that, but remember, this is still just test data that's available. We looked at vaccination thinking, well, maybe some parts of the country are vaccinating dogs more, and that's why we're getting fewer positive test results on PCR, because of great vaccination. So we did have these two data sets. One is the number of dogs vaccinated per state over that 4-year period, and on the right, the numbers per estimated dog population. The interesting thing as you look at that is you see the records that we get from the state level data on how many dogs are vaccinated gives us one picture, but when you correct that for the number of dogs per state, we get a very different picture of what percentage of the dog population is given. Once again, this is like, it always reminds me that when people show us this information, you really have to dig into what it is we're being shown, and just not immediately take it as face value. So the next slide is we wanted to look at some of the ecological and climate factors. So I think most of us were taught at one time, that lepto has a lot to do with rainfall. And if you go to the next slide, we have the rainfall data from the United States, and that's gridded out by counties, and it doesn't align with what we saw for any of the leptos testing results. And that's because it's not really about annual rainfall. It's not about mean precipitation, and we don't see a relationship with mean temperature. The lepto data has more to do with flooding, and flooding has very little to do with annual rainfall. Flooding has a lot to do with topography, how the land is shaped, and also what the land cover is. Is it forested, or is it grassland, or is it bare? And so flooding has is a much more complicated picture that some people tend to think of as linked to how much rainfall there is, but that's not really the case. If you go to the next slide. We also took the test result data and saw if there were relationships between education levels or income. So we looked at some socioeconomic patterns for all the counties in the United States. Once again, we looked at about 200 data sets, and I'll show you another picture next to see which ones lined up with where we were seeing those test results. Once again, like I said, for the hot spots, what we wanted to do is say, are there some background characteristics linked with the test result data that then we could extrapolate to see where those conditions exist in the U.S. And what we see is there is actually some relationship with the test results with income and education. Not exactly sure. I can postulate a few ideas, but remember, these are tests, or samples are submitted by clinical veterinarians for testing, and that varies by the clientele. What they'll tolerate and pay for testing certainly varies by income level and maybe somewhat by education level, and those two things we know are somewhat linked, education and income. So we might have some biases there. Next slide. This is called a partial dependence plot, and what we did for each of those variables, we plotted out how they correlated with, this is the microagglutination test, but we did it for the PCR and the MATs. So you can see that what we're able to do with this is throw out a lot of these variables that don't seem to have an effect on the test results and pick some that do. And if we go to the next slide, we end up with these types of variables became our best predictors of a positive PCR or a positive MAT. So now we're starting to get into some of these underlying drivers and ecological correlates that are associated with positive test results. So I mentioned this kind of the tree cover, the forest cover, some of those things seem to be linked with, and at the bottom on the left one is median income there. But most of them are kind of ecologically linked. And if you go to the next slide, when we project out those, this is what we start to see as a predictive model of where we should be seeing canine leptospirosis. And this is static. This is we have 14 years of data that we were working with. So when you compile the 14 years of data, you see this. If you go to the next slide, which is another video you can't see, but this shows 10 years, well, is this? Yeah, I think, no, this might be actually 14 years of data. But this is a time series analysis I can't show you. But if you look, you squint hard, you see around the New York area is a little blue, and Chicago is a little yellow, and California is a little orange. So that is for that 3-month period in the year 2000 of places that are hotter than we expected, hotter than average, or cooler than average. And as this time series runs over 10 or 12 years, if you run this out, the leptospirosis, it comes and goes. So the New York area will become hot in a year or two, and then it'll go cold again. So it really varies with time. So the disease it is not a snapshot view. You can't really predict this based on any given year, but we do actually see cycles on this. There's probably climate relationships, but it's also probably about infected, recovered individuals. When there are large outbreaks in areas, more animals tend to get vaccinated then. That probably gives them coverage for a period of time, so you see that the lepto goes away. If you go to the next slide, this is really kind of my conclusion, is that we can look at these things different ways. So on the bottom right is that original slide where I said, here are the clusters by estimated dog population of where, based on test results that we have from just IDEXX laboratory, once again, you say, oh, those are the hotspots for canine leptospirosis. If you look above that, you see where people are vaccinating dogs. And you see, even based on that, we tend to be under-vaccinating dogs in some of the places in the United States, particularly out west. We're under-vaccinating dogs for it. And on the far left, you have our predictive kind of model based on the underlying drivers of where we actually expect to see leptospirosis, irrespective. It doesn't matter where people are testing or what laboratory they're using. That's kind of what we see kind of as where the riskier areas for leptospirosis. There is no place in the United States that's zero risk. We just have places, this is relative risk, so we have places that are lower at risk and places that are higher at risk. And that's it. If you go to the next slide, we'll just finish up there. Thank you very much for your attention.
Thank you, Dr. Karish. We will now open the lines for the question and answer session. As a reminder, you may press *1 on the phone to put yourself in a queue for questions. Please state your name and then ask your question. Or you may submit questions to the webinar system by selecting the Q&A tab at the top of the webinar screen and typing in your question. Already have a couple of questions. Dr. Karish, can you expand on how climate change would expand the range of Nipah? And is it based on the best temperature range for virus or for bats? And the second part of the question is, does it also account for climate change promoting severe weather events, such as do things like drought or heavy rain come into the calculation?
Those are great questions. The image I showed, those calculations were based on mean precipitation and the mean high and low daily temperatures. And there are immediately some flaws inherent to that, and I discussed that one about flooding and things. But it's kind of the best data sets we had to work with at the time. So in answer to the second question, we didn't have the ability to look at the increase in severe weather events. And I think it probably could be done, and it would be a really cool thing to do with some of the colleagues at NOAA and NASA, because I bet they have some good projections for that. But as far as Nipah is concerned, our understanding of the ecology of that disease is heavily linked with bats and their fruit bats. So it has fruit, it's about the fruiting pattern of trees and where those bats move around, and they are somewhat migratory there. In this projection, why could Nipah get established in the New World is because of the similar genetic relatedness of bats to it, and also the ecological niche for the bats that don't exist currently in the New World of them becoming established here. So it might involve the release or the introduction of a host species of that same bat into the New World. So some people would say, oh, well, that'll never happen. But if you think about reality, as we have a couple of hundred invasive alien species now in the New World that have been introduced in the last 100, 200 years. So the introduction of new species is not a very rare event. In fact, it's somewhat of a common event. And that allows the host, what those projections are really saying is the kind of the guild of types of bats that we know can host the Nipah viruses or related to them. The ecological conditions would exist in those areas in the New World and in Europe to allow those species to flourish, where currently they wouldn't do as well. I hope that answers the question.
All right, we have another question. What are some of the informatic approaches that can assist with prevention, treatment, and control of EID events?
What are some of the, what type of?
Informatic approaches.
Informatics. Well, I'm not sure I understand that question quite right. But if it's about information sharing and data sharing and education and outreach, I'm just going to go down that line thinking I'm understanding this. But I think, I'm kind of an old-fashioned guy. And when everybody goes like, oh, there's this new disease, and we don't know how to treat it, and we don't have a vaccine, I start to put them back in those categories that I talked about and said, well, is it foodborne, is it vector-borne? And we actually do know some things about how to prevent those diseases. And what we seem to fall down on is sharing that information, getting it out to the public. So Ebola, you go like, oh, that's really horrible. But if you never teach people how to avoid getting it, and that's rural community education and outreach, then we'll never get it under control. And in communities in the Congo, I've worked in northern Congo. We did education programs in the whole northern half of the country to every village and explained to them that if they see a sick or a dead primate, non-human primate, don't touch it and don't eat it, and stay, don't mess with the bats. And they were so appreciative because no one had ever told them, how they could reduce their risk of getting Ebola. No one, so that's not a hard thing for them to avoid. Their diet is not dependent on eating gorillas. They just do it because it's opportunistic. They find it and they see one, they do it. So I don't know if that's informatics, but I think as we get out, I'm going to link that somehow to text messaging and cell phones, because as you go through Africa now or through Asia, everybody is better connected. And I think these opportunities exist to start really educating the masses and not, the public health, either veterinary public health or human public health, the burden of that can't just fall on medical professionals. We have to find good ways to share that information to engage the public so they can pick up part of that responsibility. And it also goes to other sectors of society, too. The food industry is aware of it more than many, but even the Department of Water and the Department of Education need to be much more engaged in health promotion and sharing information. I hope I at least skirted close to to that question. Sorry.
Thank you, Dr. Karish. Why don't we take a break and see if there's any questions through the phone? Amber, are there any questions on the phone?
We do not have any phone questions yet.
Okay, then we have another question. Dr. Karish, can you address the concerns about the ongoing Nipah infection with the tradition of drinking raw date palm sap? Meaning, how do you educate folks about how they can protect themselves from zoonotic diseases while respecting traditions?
Yes, that's a great story and a great example of community engagement. So for some of you who don't know that Nipah virus in Bangladesh, not so much in Malaysia, it has a different transmission pattern route, but in Bangladesh, Nipah virus goes from fruit-eating, nectar-eating bats into humans because humans collect the sap of date palm trees and drink it. And they'll put an urn or a bowl or a jar. They'll climb up in the tree and they'll cut it just like we tap a maple tree. They'll tap on the side of the palm tree, and then they'll tie the jar or the urn there to the tree and leave it overnight, and the sap will run into that, and it's kind of a light, juicy, sweet sap, and they like to drink it. Well, during the night, the fruit bats also come in, and they eat or drink the sap also because it's sweet and it's tasty. And while they're there, they potentially contaminate these pots that are collecting the sap with urine and feces and saliva. And then the human outbreaks come from when people drink this sap. Now, one thing, of course, you could do, like we do with milk, is pasteurize or boil the juice before you drink it. But local people, they don't mind that, but for them, it doesn't taste as good. It does change the flavor, and it doesn't bring the same high price as the fresh juice does, and they like to drink it very fresh before it starts to turn alcoholic, in the case of Bangladesh, where they don't drink alcohol. So one thing is just to educate millions of people. The challenge in Bangladesh is one of the most densely populated places in the world. On the positive side is not everybody harvests. There's a limited group of people that harvest sap. CDC working with there's a Bangladeshi Institute for Research on diarrheal disease, really long established, and CDC's been working on them for years, did some very cool work, and EcoHealth Alliance is involved with that a little, but the CDC, the Bangladeshi partners there, did some great work using infrared cameras at night to watch the bats and really documented this contamination of the sap. Step two was to come away, well, maybe if we can't get them to heat the sap, maybe they could kind of protect the pots. So some of them there developed this idea of making these skirts out of bamboo to cover the pot to keep the bat out and keep the urine and feces out. And it costs maybe 10 or 15 or 20 cents for a little bamboo skirt, and they can cover the pot, and then that reduces the risk. And the added benefit for the people collecting the sap was the sap is cleaner, and they can actually sell it for a higher price, because when they collect it in the morning, there's not feces floating around in it. So it's a little cleaner, they get a little higher price, and they reduce their disease threat. It's not a perfect system, but it's that kind of innovative thinking. It's certainly cheaper than trying to develop a new vaccine for Nipah and vaccinating millions of people. Over.
Amber, are there any questions on the phone line?
We do not have any questions on the phone lines at this time.
Okay, thank you very much.
We've run a little over time. My apologies.
Oh, no problem. It was very interesting and insightful information. Thank you so very much. On behalf of CDC's clinician outreach and communication activity, I would like to thank everyone for joining us today with a very special thank you to our presenter, Dr. Karish. If you have additional questions about today's call, please email us at coca, C-O-C-A, @cdc.gov. Put May 12th COCA call in the subject, and we will get an answer or response to your question. The recording of this call and the transcript will be posted on the COCA website at emergency.cdc.gov/COCA within a few days. Free continuing education credits are available for this call. If you would like to receive continuing education credit, you should complete the online evaluation by June 11th, 2016 using course code WC2286. For those who will view the archived webinar after June 11th, please complete the online evaluation between June 12th, 2016 and July 11th, 2018 using course code WD2286. All continuing education credits and contact hours for COCA conference calls are issued online through TCE Online, CDC's training and continuing education online system at www.cdc.gov/TCE online. Again, that is www.cdc.gov/TCE online. To receive information on upcoming COCA calls, please subscribe to COCA by sending an email to COCA, C-O-C-A, @cdc.gov and write subscribe in the subject line. Also, CDC launched a Facebook page for clinicians. Please like our page at facebook.com/CDC Clinician Outreach and Communication Activity to receive COCA updates. Thank you again for being part of today's webinar, and we hope everyone has a nice day.
Thank you. That concludes today's conference. Thank you for participating. You may now disconnect.